In this video, we are going to work on human face landmark detection project, where we are going to input the human face and the model is going to predict 106 landmarks. Hello friends, welcome to this video. This is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel and hit that bell icon for more such videos on deep learning. So first of all, we are going to take a look at the dataset which we are going to use for this project. So here's the folder containing the dataset along with the research paper. So the name of the research paper is a new dataset and boundary attention semantic segmentation for face parsing. So the name of the dataset which is introduced by this paper is Landmark Guided Face Parsing dataset, that is LaPa in short. And in the figure 1 you can see the input image, the landmark points and the multi-class segmentation mask. So these are the three things which is introduced by this dataset. But for this project we are interested only in the images and the landmarks. I have already done a video on image and the mask, so you can check that video, and the name of the video I think is human face segmentation. You can check the description for that video. So this is about the paper. If you are more interested in this paper, I'll give the link of the paper in the description. Do check it out, and maybe in future we can implement this paper also if you want me to do. So if you want me to implement this paper, then just write it down in the comments, okay, and I'll try to do it if you want. Now let's take a look at the folders. So first we have test, then training and the validation. So all the three folder contains images, labels and landmark subfolders. So images would contain images samples, you can see a wide variety and range of images having different resolution and conditions. Then we have labels. So labels refers to multi-class mask. So these are normalized masks. Maybe you cannot see them very clearly here because they are normalized. We are not interested, let's leave them. Then we have the landmarks. So here you can see for each image we have a text file associated with it. Now this is a text file. If I go up at the starting of this file, you can see a number, that is 106. So in each file we have this number at the line 1. So 106 refers to the number of landmarks for the face this dataset provide. And from the line 2 to line 107, if you see, it has two numbers. First refers to X and second refers to Y. So these are the coordinate point, that is 106 coordinate point for the human face. And we are going to use these landmarks for our project. Now let's start with the code part. So first of all, we'll start by importing all the libraries which we require. So first of all, let's import the OS library, that is one of the essential. And in the second line we have this TensorFlow environment variable, I think. So I usually write this to get rid of all the messages which comes with TensorFlow when you try to run it. Okay. After that we are going to import the NumPy. So let's import the NumPy. As we are dealing with images and images are arrays, so that is why we have imported NumPy to play with those arrays. Next we are going to have the CV, OpenCV, not CV, OpenCV. This is to read, resize and write the images back to disk. After that we are going to import the globe function. So globe function basically takes a path, and with that path we give basically a pattern. Let's say we have path and then we say star. So it basically means it matches the file path with that pattern and extract all the path. Okay, and I'll show you how it works in the when we move to that part. After that we import the TensorFlow. So let me directly copy all the things from the TensorFlow. So here we first import the TensorFlow, then we import the layers, okay, SL. After that we have imported this MobileNet version 2. So this is the network which we are going to use for this project, that is MobileNet version 2. Maybe you can use any other architecture which you like. Let's say ResNet 50 is much better than MobileNet version 2, but I am trying to here build a lightweight thing. I'm just using it from the perspective that maybe we can use it for videos or webcams for real-time feeds. So for that thing, we need a really lightweight architecture which has less parameter and works in real time. So with this architecture, the performance may be low, but because we are trying to work with real time thing, maybe more videos would come on this landmark project with some real time work, maybe on videos, webcam, maybe not on webcam because I don't have a good quality webcam and my condition of my room is not that I can show you. But still, it would take time to have some videos with webcam. Okay. And at last, we have imported all the callbacks. So these are the 4 important callbacks which I use in most of my TensorFlow projects, and explain each of them to you. Next, we have some global variables. So first we have the image height, then we have image width, and then we have the number of landmarks. So for this project, I'm going to resize all the images to 512 by 512 because I have a RTX 3090 which have 24 GB RAM that is VRAM. So I can train image model with such high image size. Maybe you don't have access to this strong GPU or computation, so you can resize the images accordingly. Okay, so this is not compulsory for you to use 512 by 512. Maybe you can use 128 by 128 or 256 by 256. Okay, or even 320 by 320 is fine. Okay, so just choose the image height and width accordingly. Next, let's have a function called create dir. So this function takes the path, then it check if that path exists or not, and if that path does not exist, then it's going to have that path. So basically it takes your path and create that path if it does not exist. So we use it to create blank folders, because during training we're gonna have wait files to save. So that is why we are going to use this function to create a folder for us, and we're going to save our files in that. Okay, next let's have a function to load the dataset. So this function is going to take one argument, that is the dataset path. So here we are going to load the training images, its landmark, and same we're going to do for the validation and the testing set. So first of all, let's import the training images. So train refers to training and x refers to input or the images, or in short you can say x refers to input image, and here y would refer to the landmark. Okay, now here we are going to use our globe function. Next we need to provide path to it, and for that I'm going to use OS library. So first we have path. Now let's move on to our folders. So here you can see we have train. Okay, so let's write train here. Okay, let me just do train, and we need images. So let's go back to the folder. We have images, and then we want to load all those images. Okay, let me just reload them again. So it would take a bit of time. Till then work with our code images, and after that here we're going to write star. So this is basically a pattern at the last. This is the pattern star. So star basically means get everything. Okay, now move back to a folder. So here you can see it's gonna load all the images. Even if it has by mistake some text file, it also going to load that, and that would cause error. So for much better image extraction, you can say at last.jpg. So it basically means the image file or whatever item is inside that folder should begin with anything, but it should definitely end with .jpg. So it's going to get all the images path as a list in trainx. Okay, then because it's a list, so we're going to sort that list. So we have all the names in a specific order. Now I'm going to copy this and we're going to paste it. So I'm going to say train y, and if you remember, for labels, not labels, the landmarks, we require the landmarks. These are the labels for us, landmarks, and it has text file. So we're going to say .txt. So now we have training images and the training landmarks. So same we're going to do with validation and testing also. Valid, valid, and here we're going to say, okay, let me just copy it from here only. Valid. Okay, let's check the name whether it is valid or val. Okay, it's val. I just got it before I just do a problem. And next we're going to do same for the test. Okay, then we give those training, validation and test image and landmark back. Okay, so this is done. Now let's try to execute these to check. So we have our main function here, if name equals to main. So first of all, we are going to seed the environment. We're going to seed the randomness. Then we need a folder to store all our files, as I've already told you why. To save our weight file and other files which would be built or stored during training. Okay, then we require some set of hyperparameters. Okay, so here we have image height as 512, image width as 512, landmarks 106, input shape is this 512 by 512 by 3, as we are going to read the image as RGB. Then we have batch size as 32, so you can decrease the batch size accordingly. Okay, this is it. These are the parameter which you can change. I think you cannot change this landmarks because these are fixed. I think rest you can change. Image height and width you can change accordingly. Batch size would also change accordingly. Okay, according to your system require or your hardware specification. Then we have learning rate, and then we have number of epoch. But okay, next we have some paths. Okay, so first we have the dataset path. So I'll provide you link for the dataset in the description. So from the description you can check the link and download the dataset. Next we have the model path, where our model file, that is weight file, would be saved. It would save inside the files folder. The name of the file would be model.h5. Next we have the CSV path. So this is the file which would be created during training, and it would save like training loss, validation loss, learning rate, etc. Okay. Now we are going to load the dataset. So we have called our load dataset function, and it gives back the training, validation and testing. Then you print the size of each of those, that is training x, train y, valid x, valid y, test x and test y. Okay, so let's just execute this program. Here you can see for training we have 18,168 images and landmark. For validation and testing we have 2,000 images. Okay, so I think the dataset is really big enough for you to work. Maybe you can decrease the number of images in training because these are really high. Because if you don't have good computation resources, so it would be really time taking to train that model. So you can tune these things accordingly, like image size, batch size, number of samples. Okay. So we are done with this. Next we are going to build the dataset pipeline. Okay, so first we are going to build a function to read the image and those landmark point. So we're going to call it read image landmark. So it's going to take the image path and the landmark path, that is that file. So first of all, let's read the image. I think that is reading the image would be really easy if you are my subscriber or you know a bit about the OpenCV. So we say image equals to cv2.imRead. So this is the function which would help us to read the image. We were going to give the path to it, and it's going to give us a numpy array. First image path. So if there is any error in this path, it will not give anything back. Okay, after this line we have resize. Because this is blank, the resize would cause an error. Okay, just remember that. Then because we need to read this image as RGB, so we're going to say cv2.imRead underscore color. Okay, Then here we need to save the height and width of the or input image, because we are going to resize it. So before resizing, we want to know its shape, because we require this original height and width to normalize those landmarks coordination point. Next, let's resize the image, then image width, image height. Now if you are confused from where these two value come, argument, the function argument don't have, so we have already specified them as a global variable on the top, so any function can access these values directly. So we have resized the image. Now we are going to normalize the image by dividing it with 255. Then we're going to convert it to float 32. So we are done with image part. Let's print shape. So let's call this function at bottom for now, and give it an image path, that is training. Then train y would contain the landmark file. Okay, so let's execute the okay, here you can see the image is resized to 512 by 512, and we read it as an RGB. So this is why it has 3 channels. Now we're going to work on the landmark. Okay, so first of all, we need to get the data from the file. So we're going to say data equals to open. So this is a function to read a file. So we're going to give the landmark file path, then we're going to read it as a simple text file, then we're going to say read. So this would give us the complete data. So let me just say print data, and I'm going to print everything on the screen. So here you can see this data points get printed on the screen. Okay, now we are interested in rest of them, we are not interested in the top one. If you see, these are like first we have some value, then move to next line, then next line, then next line. Okay, so we can split this entire data because it's a string. So what we can do, we can split it. Okay, so first of all, before splitting, let's have a empty list, the landmarks. Okay, this is where we are going to save all our coordinate point. So we're going to loop over our list. I'll show you what list. Data.strip to remove any spaces, the beginning and end. Then we're going to split it on new line character. Okay, I hope like you understand this thing. I think it's not that complex. So this is a loop. Now it's going to print each line. It would still appear the same, but this time it's going through a loop. So at first it's going to print this. Okay, let me just make it a bit easy for you. What I'm going to do, we have an index variable here. We're going to say index plus equals to 1. We're going to increment it. Then we're going to say idx. So we have this value every time. So you can see now 106, 105. So these are separate lines. So what we need, okay, we are going to remove this. So what we're going to do, we're going to say from 1 everything. Okay, we are slicing it here. Let me run it again. So this time if you see, we don't have that 106 at the top. So now this is one string. Okay, we are going to split it on the base of the space, because this is the space is separating them. So we're going to say x comma. Okay, let me just do it much simpler for you. You can say line equals to line dot split that space. Now I'm going to print line. This would be a list. You can see a list. At index position 0 we have x, at index position 1 we have y. So what I can say, x comma y. Now these x are strings, so we're going to say let's convert them to float. So if we see, these are numbers, okay, and they can range from 199, 178 to like 207, 17, okay. Now we are going to normalize them. So what my way of doing this project is that I'm going to convert these number in the range of 0 and 1. Now you may ask how you're going to do that. So that's a really simple way of doing that. So the x, basically what it is, so like what is the maximum value x can get for x, any x coordinate point, what is the maximum value we can get? That maximum value can be width of the image, okay, that is the maximum value. And for y, what maximum value can we have for y is the height. So we're going to divide the x with width and y with height. So this way we're going to get a normalized value. So let me just print them. Now see, so you can see you have get a value between 0 and 1. So no value here would be greater than, or you can say equal to 1. It would be either equal to 1 or greater than or less than 1, okay. In so these value are in the range of 0 and 1. See every value, you don't gonna get any 1 or more than 1. The maximum possible chance is to get a 1, not more than 1, okay. So this is how we normalize those values. Did you get it? So this is one of the important thing here. If you see, now these values are normalized, so model is going to give us normalized value only. So then during the testing phase, when we gonna get these, so we need to multiply them with the these height and width. Make sure we plot them correctly on the input image, okay. Now what we're gonna do, we're gonna append these two values in the list. So now our output would be a list, and that would contain values in the sequence, let's say x1 y1, x2 y2, x3 y3, x4 y4. So this is list is going to have a length of 106 by 2, okay, because we have 106 point, and for each point we have two values, that is x point and the y point. So it would be 106 by 2 into 2, not by 2, okay. So we have landmarks here. Now what we're going to do, we convert this landmark into a array, because it's easy to work with array. Then where we're going to say the data type, not axis, and we're going to convert it to float 32, because if you see, all those values are floating point value. So don't just convert them to integer. If you convert them to integer, that would have a bit problem. So values less than 0.5 would be 0, and more than 0.5, I think they would be converted to 1, or they can also become 0. So just remember that thing, okay. So now we have both image and the landmark. Let's give them back. So let me just say image and landmark, okay, and I'm going to print both of the shifts once again. So let me just print them here. Should be L, not landmarks. That is my mistake. You can see the landmark points and the input size, okay. So now I'll show you how you're gonna plot them on the images here only, okay. So let's have a function, okay. Let's write a function here. So this function we're gonna call plot landmarks. First, what it would take, the image it would take, then it would take the landmarks, those normalized points. So just assume we have these two. So let's we're gonna take train x. Okay, so we need to read the image first. Okay, we're gonna say this I only, okay, I and the L. Now what we're gonna do, we're gonna plot those points on this L. So this I image is also normalized, okay. For just let's remove this line, okay, because we don't want the normalized image for now. I'll tell you what I'm doing, why I'm doing this. So let's go back to our function plot landmarks. So what we're gonna do, first of all, we're gonna save the height and width. Then if you remember the list, okay, it is x1, y1, x2, y2. To plot a dot or a small circle on the image, we need these 2 points. How are we going to proceed? So we're going to have a loop. We're going to say for I in range, it start from 0, go to the length of the landmarks. Then we're going to have an increment of 2. First it would give you x1, then x2. Okay, this I would be 0, then 2, like this is going to do. So let me just print the value of I for you. We save it and run it for you. You can see 8, 10, 6. So this is a gap of 2. Now let's have the x. So it would be landmark I and y is equals to landmark I plus 1. Got it? Now these are normalized value. So let's say for this image, you have this specific height and width. You want to plot those landmark on this image. So this image can be any image, okay? Just you need to have its landmark with respect to this image. The height and width of this image can be anything. Just multiply them with x with width and y with height. So now you need to convert them to integer. So now these are again convert back to the with respect to that input image height and width. Now what we're going to do, we're going to say image equals to cv2 dot circle. First input image where we want to plot those points, then x comma y, then we need a radius for a circle. Let's say for now, let's say 5. Then RGB code for the circle, let's blue. Then we want to fill the entire circle. So we have this image, let's give it back. So it is going to give some image, let's say img, and we need to save this image. Okay, one more thing. Yeah, it's done, it's done. So first a path, we can say landmark.png, then img. Okay, let's see if it work. I'll show you where the image is. Okay, landmarks is not defined. What do you mean landmarks? Okay, let's check our function. What problem does it have? Let's go a bit down. What is landmark? Okay, it's landmark. Yeah, I get it. Why this error? Okay, it's fine. We don't have any error. I assume it works. Okay, if you see this image, it has all those 106 landmark point on this image. Did you see it? And it's of size 512 by 512. What we can do, we can decrease. So you can play with this value accordingly. Let's say 2 here. If I run it again, should work. I can see those points. They are now, it's fine. Now the size of this image is 512 by 512. Now let's change the size of the image. We'll go with the original image size, but before that let me uncomment this part, because this is for Dataset API part where we need to normalize the image. This I, for now, what we'll do, I'll take this, I'm going to read this. Okay, so I'm going to print size of this image. Okay, so this would be a bit different from the origin, the one we have seen, that is 512 by 512. So let me run it. You can see it's not 512 by 5, it's less, 492 by 440, and it has worked. Now you can see image size is different, but we have same landmark points, you see. So this is how you're going to convert those normalized point back into a form which you can in which way you can plot them. So let me just remove this part of the code. This is done. And now we need to work on the dataset part. The dataset API we need to work on. Okay, we don't require this part here, so we're gonna. Okay. So first of all, we're gonna write a function called preprocess. So it's gonna take x and y. X refers to the image path, y refers to landmark file path. Another function f is gonna take x and y. X and y again means the same, image path and the landmark file path. Because this preprocess function is going to be used inside the TensorFlow API, so those x and y would be encoded. So we need to decode them. Okay, so we have decoded them. Now we're going to use our read image landmark function. So it's going to give us image landmarks, and we're going to give x and y as the input. Now this function is going to give back these two things. Now if you see, this is the f. This f function uses a lot of things like numpy, OpenCV, which are not inside the TensorFlow. To use this function inside the TensorFlow, we have a special function called tf.numpy function. This function, first of all, take the name of the function which you want to execute. We want to execute a f. Input would be xy, and next it would take the data type of the output values. So data type for this image and the landmark. So it would be float 32. Now this is going to give two values back again, image and the landmark, but in tensor form. Now we need to specify shape for those. So shape for the images, image height, image width, and number of channel as 3. Then for landmark we need to set the shape. For this it would be num landmarks into 2, and you know why into 2. And now we're going to give these image and the landmark as output of this function. So we have this done. Now the last function is remaining, and that is called tf.data. It's also going to take x and y. Here x and y refers to list of images and y refers to list of those. Okay, x refers to list of images path and y refers to list of those, what do we call, the landmark file path. Yeah, x and y, then batch. By default let's give value of 8. Now I'm going to say ds tf.data.dataset from tensor slices. X and y as a tuple, then ds is equal to ds.shuffle. So first of all, you're going to shuffle the data set. Here we need to set a buffer size, let's say 5k. Then we're gonna map those values using the preprocess function. Then we're gonna convert them to batches, and then at last we're gonna prefetch some values, like during training one batch is using training, another we're gonna fetch some batches in advance so that it optimizes and it take less time to train. Okay, now we're gonna give the ds back. So this simple function. Now we are done with our dataset part. Okay, now what we're gonna do, we're gonna build the dataset API, not the API, the pipeline, you can say. So this is training dataset, validation dataset. So what they take is train x, train y, then batch size, then valid x, valid y, and the batch. Simple. Now let me just show you what they have. Train ds. These x and y are basically batches. Okay, batches of images and the landmarks. can see batch size is 32 and height is 512 with 512, and same if you can see the number of points now double to 212, that is 6106 into 2. So we'll interrupt them because that is our this is not our main task. Now what we're gonna do, we're gonna build our model. For this task we have already imported, if you remember, the MobileNet version 2. So this is what we're gonna use. Let's do it here, call build model. So it's gonna take two things as the argument, input shape and the num landmarks. So first we need to build the inputs layer, l dot inputs. It's gonna take the input shape, then we're gonna have the backbone. So it's kind of transfer learning we are using here. So for MobileNet we're gonna say include top to false. We don't want the classifier, we just want the feature extractor part. Weights is equals to ImageNet. Then we have the input tensor, that is input to this architecture, that is our inputs layer. In MobileNet we have one additional value, that is alpha. So this alpha helps to increase or decrease the number of filters, and that would directly affect the size of the model, the number of trainable parameter, training time. So here we're going to say 0.5, I think we have, yeah, 0.5. So I think there are 0.5, 0.35, 0.75, then 1.0, then 1.4. These are the alpha values. Okay, now we need the output from this backbone dot output. So this is the output of this. So let me just call it at the here. So first input shape, num landmarks. Okay, now what we'll do, we'll print the x. Okay, it's still, yeah, it's done. Okay, it's my mistake, it should be capital, I should be capital here. Again mistake. See, I'm doing a lot of mistakes. Now I think it should be fine. Okay, you can see it's fine. Now the output of this MobileNet version 2 has a shape of 16 by 16 by 1280. So what we can do next, first of all, let's say make sure that this backbone is trainable, because we are going to train the whole architecture. Okay, then we're going to pass this output of the backbone through the global average pooling. Now let's print its dimension. Now it's 9 by 1028. Now what we can do, we can have a dropout here, 0.2. Then we have our output here, you can say dense. Okay, it should be L dot dense, otherwise we would have another error. Num landmarks into 2 activation is equals to sigmoid. Now you may ask why sigmoid, because if you remember, if I show you, our landmarks are in the range of 0 and 1. You see here they are in the range of 0 and 1. So when you so what sigmoid function does is it give our output that is in the range of 0 and 1. So this makes it easy and compatible things with each other. So prediction is compatible with the ground truth. So it's really easy for the model to learn things. Now we're going to build our model. First we're going to give the inputs layer then outputs layer, and we're going to give this model back. Okay, so we are done with the model building part. So we're going to say model. Now we're going to compile this model. Okay, so model.compile. First we need is loss function, because if you see, it's a kind of a binary classification, not the classification task basically. So it's a binary task if you see, because we are using sigmoid. Okay, so for this we're going to use a binary cross entropy. Then we need the optimizer, and here we're going to use the Adam optimizer. Inside it we're going to specify the learning rate. Okay, now comes the training part. So we'll here specify some callbacks. Here are 4 callbacks, and I explain you each of them. So first is the model checkpoint. So this callback helps you to save the weight file during training, and it only saves, okay, let's say monitor values. Yeah, let's specify it here. So it's going to monitor the validation loss. If it decreases, it's going to save the checkpoint to the weight file. Then we have reduce LR on plateau. So this also monitor the validation loss. So it has a patience value of 5. So let's say for continuous 5 epoch, the validation loss does not decreases. Then it's going to decrease the learning rate by the factor, that is 0.1. Then we have CSV logger. So it's going to save all the training loss, validation loss, learning rate, number of epoch in a CSV file, so that later when the training get completed, we can check what our values are, or we can use that CSV file to plot graphs also for our research papers, and also for better visualization. At last we have early stopping. So this is a mechanism to stop the training. So we don't have any fixed number of epochs, okay, here. So what we does, we monitor the validation loss. Let's say for a continuous of 20 epoch, the validation loss does not decrease, then the training is going to stop. So these are our 4 callbacks. Now we'll call our model.fit statement, where we provide training dataset, validation dataset, number of epoch, and finally the callback. Okay. So this is done. Now we have it's time to train our architecture. So you can see it's showing some warning, but don't worry about it. It's gonna work. We're gonna have good results. So till the time it's trained, let's work on our test file. Okay. So in this, so first of all, let's import some things from the training, because they are going to be common. Let's go to the top. Okay, so first of all, let's import till here. I think this is we gonna require. Okay, so let's import one more library here, that is tqdm. So tqdm is basically a progress bar. So what it does, it's gonna give you a progress bar on the terminal, so that you can see out of, let's say, 2000 images, how many images are done. Okay, so this is just show you how many iterations are done in a loop. Then we're gonna copy, or you can say cut a function from here, because this paste. Yeah, this plot landmark function is not required here. Basically this is just for the demonstration. In training it is not required, so we have it here. Now we're going to copy some few more things from the training file. So these are basically common things, so we are not going to do them again and again. So first we want to seed the environment with same seed number, and then we're going to create a folder called results, where we are going to save our images on which we have plotted the landmarks. Then image height, width, number of landmark, then the dataset path, model path, and finally we load the dataset. So till this everything is fine. Next, we are going to load the model. So we're going to say load the model. Model equals to tf.keras dot models dot load model. And here we need to provide the path to our model file. That is the weight file. So okay, so first epoch is near about done. And when this epoch is done, we're gonna have our weight file, okay, and the CSV file with us. I'll show you how those looks. So this is our model. Because we are already using our GPU in training, so I cannot show you this we cannot run this test file for now. We'll run it later. Now let's move forward, move on to the prediction part. So for this testing, we're going to use all the images, all the test images, okay, and compare them with this test y. So what we're going to do for x comma y in tqdm. So this is the progress bar which we're going to use. Okay, let me just inside it we're going to write zip test x test y. So these x and y indicate each item from this list, test x and test y. Then total another argument for this tqdm would be number of iterations, and that would be equal to length of list x or y. Okay, so this first epoch is done. I'm going to stop it. So for first epoch, the validation loss improved from infinity to 1.10. Okay, so let me just show you. So this is the files folder, and inside first we have this data.csv. And if you see it as epoch, training loss, learning rate, and validation loss recorded for us. And after that we have our model.h5 file. And if you see its size, it's really small, that is 12.5 MB. Okay, so that is why I've used it here. Okay, one more thing, I've already trained my architecture, okay, on this data set. If I show you 22 epochs, if I show you now, what I'm gonna do, I'm gonna copy these two files because I don't want to train it anymore. It would be time consuming. So we're gonna use these train file, and I'm gonna provide you the train file in the GitHub code. So don't worry about that because the file is really small, so I can provide it easily to you. So inside this loop, first of all, let's print the x and y. Okay, so these are the paths, but still we're gonna print them. And let me just break the loop here because this is loop and it's gonna run if I don't stop it. Okay, so first of all, okay, we need to import some libraries we haven't imported from the training. So let us run this program again. It prints the number of training, testing, and validation. Then it prints the model, and here you can see the number of parameter, and at last you can see the path, training image path and the text file path. And if you see, both image and the landmark file have same name. So what we need to extract this name. Okay, we just need the name because we want to save the file, so we need a name. So what we're gonna do, I'm gonna print x again, and this time we're gonna remove this line. So this is a string, okay, because I am using a Linux system, so my slash is different. Maybe if you are using Windows, so you have a different slash. So what I'm going to do, I'm going to use the split function and split it on the base of the slash. So just remember, this slash can be different for you. Name x is a string, so we're going to split it. Okay, yes, okay, now this name would basically be a list. Okay, you can see it's a list, and if you go to the last, It is the name with extension. Okay, so what we can say, -1. Now you'll see we have the name and the extension. Okay, so we are fine with this. But if still you want to extract the name, what you can do, we can again split this string on the base of dot. Let's do it. Split. I hope you understand the concept here. Okay, if you understand the concept, then it would be really easy for you to implement it in any operating system. Now you see image and then the extension. So the 0th index we have image. Now you're gonna have the name only. So this is the name. So we are done with this part. Now we are going to read the image and the landmark. So first of all, we're going to read the image, and I'm going to directly copy it here. Reading the image. Okay, let me write a line also. Okay, so we read the image X, that is the path, as RGB. Then we make a copy of this in image underscore X. Then we resize the image, normalize the pixels, expand its dimension. So till here, the size is, if I show you, it's 512 by 512 by 3, because the model takes the input in the form of batches. So this is only one image, so we make a batch of 1 by doing this. The axis 0 means we expand the dimension of this array on the 0th axis. It became like this. So this is a batch containing one image. Then we convert it to float 32. Now we are going to read the landmarks. So again, same way, we read the image, we get the data, we have the landmarks. Same procedure if we see, but here we again normalize these X and Y. Okay, by dividing them with original image height and width from image underscore X, not image, because this image is resized, but we have taken the height and width from this image underscore X. Then we again append them to X and Y. Then we convert them to float 32. Now we need to make the prediction. So let me write the code here. So we're going to say prediction. So we're going to say pred, that is the prediction. Model dot predict. Input would be image. Verbose is 0. Now I'm going to print the shape for the dimensions of this prediction. Okay, you can see, because in input we have given one image in a batch, so output would also be with corresponding to that one image. So it gives you 212, that is those coordinate points. So let's convert them to float 32. They are already should be in float, but still we can specify them so that we know. Now if you remember this function, this plot landmark, we're going to use this function. Okay, so we're going to say saving the results. There is a mistake. So what we're going to do, we're going to say first plot the landmarks for the ground truth. We're going to give image underscore X, copy of this image, then the landmark. Then we're going to do it for the prediction. Plot landmarks, image X dot copy, then prediction. Okay, now we have both the ground truth and the prediction. So we're gonna concatenate these two images and make it a single image so that it's better for comparison. But in between those two images, we're gonna have a white line separating them two. So we're gonna call that white line the simple line, and we're gonna use numpy array and we're going to fill that array with ones, and the shape of that array would be image x dot shape 0. Then 10 is the width of that, then 3. Just wait few seconds and you're going to understand what are we doing. Now we're going to concatenate these images. np.concatenate. First we have this ground truth landmark, then we have this line separating them, and then we have prediction. So this way you can easily compare both. And now we're going to save it. So first, the path where we are going to save it first is results, the name of the folder, the name of the file, and you'll see cat images. I hope this should work. Let's now run it for one, because we have added a break here. Okay, so it has some issue during concatenation, if you see. So let's do one thing. Just print the shape of each of these. Okay, and then we'll see which one have error. The error is okay. I know what the error is because of this, my mistake. So axis should be 1, not 0. I think it should work now without any error. Yeah, the program has stopped. This means it is working. So we go into this folder, we have this one image. Okay, if you see, so these dots are a bit tiny. Okay, we need to increase the radius of this circle. Even if you go to this prediction and see, we have this dot at approximately right place. So let's do one thing. Let's have a radius. I think my mouse is not working fine. It's not that smooth. Please guys, just help me with the mouse, because my mouse only works for about of 6 months. So just give me some link of a good mouse which works up to 1 year at least. Like within 6 months mouse is dead. So I buy cheap mouses only. Because it's not good to have expensive mouse. Okay, so what are we going to do? We're going to take the height of image and multiply it with like a very small number. Okay, and we're going to convert it to integer. So this would be radius. So this radius according to the image height and width. I think that would be much better. Okay, so let me run it for all the images, and then we can easily see for all how does it perform. Let's hope this will not be any error. So now if you see, this is the effect of TQDM. Now you know after 2000 images 74, 78, 100 are done, and this time it has taken, and this more time it's going to take, and these are the images per iteration is showing. This is number of iterations per second is showing. Now let me okay, here you can see. If you see, now you can see dots are fine, and if you compare the ground truth with prediction, they are near about same. You can say they are nearly the same, and it's giving perfect results, accurate result, you see. And dots are also fine, they changes according to the size of the image. Okay, and we are just doing them on the original input high image, because these images are changing. Okay, we have one error here. If we see our prediction, it's a bit down from the face. Okay, and I believe it's trying to predict the symmetry between both left and right. If you see, in left it's also bulging a bit, in right it is bulging more. So this is one of the bad example we have, and here also it's a bit out of phase. Okay, but I think it can be improved, because we have only trained it for I think 22 epochs, and with MobileNet version 2, so you can change the architecture to, let's say, ResNet 50, train it on more epochs, you can apply data augmentation, so that would give you better results. But I believe with what I have is much better. It's really good result, I can say. It's not that bad. This example is really looking good, even because it's a grayscale also. So model works on grayscale also, because it has some images in grayscale also. That is good. Okay, so the results look fine to me, and I don't have any problem with the results. So this is about the human face detection. I hope you enjoyed the video and learned something new, and maybe you can use it in your project, or maybe it has helped you in some project, research paper, or anything. And if it helped you enjoyed the video, then please make sure you like it, share it with your friends, and do comment out how do you feel about the video, or if you have any query, any problem, please write it down in the comments. And at last, I want to say, do subscribe the channel, okay, and watch my other videos also. Thank you. Have a nice day.